All right, in this lecture, we're gonna start discussions on forces and Newton's laws. I don't think I need to explain forces, right? Everyone is familiar with forces. We use this concept every day. A force is pretty much like a pull or push, right? And then there are actually two different kinds of forces we see in every day, okay? One of the forces is the contact force, okay? So if you want to push anything, pull anything, you want to kick something, right? You definitely need to be in contact with this object. There are also other forces that don't require contact, like gravity, okay? We feel gravity every day because of the Earth, but I don't need to stand on the ground to feel the ground, right? You get onto an airplane, okay? You still feel the force from the Earth on you. So gravity doesn't require contact. We call these forces field forces. Electric force, magnetic force are field forces as well. They don't require contact, okay? If you're gonna take Physics 2, you're gonna study these two forces in detail in Physics 2. What is the relation between forces and motion of an object, okay? So this was discovered by Isaac Newton. So in 1687, okay, that was over 300 years ago, Isaac Newton published this book, Mathematical Principles of Natural Philosophy. So that was a milestone in human history, because he summarized the relation between motion and forces in three laws, only three laws. Okay, now we call them Newton's laws. Okay, he laid out the foundation for classical mechanics. Okay, and the groundwork for modern science. Okay, and then he also invented calculus. He discovered the first type of fundamental force in human history, gravity. He also discovered the law, okay? So he has revolutionized our understanding of the world, okay? His contribution to science was monumental. So that's why a lot of people credit him as the father of modern science, okay? So anyway, so that's what we're going to study, okay, Newton's laws, okay. So the first law is this, is the law of inertia, okay. An object will remain at rest in uniform motion in a straight line unless acted by an external or unbalanced force, okay. So that means any object, okay, in a motion doesn't actually require a force to keep this object in motion, okay. It's going to keep moving with the same velocity, okay, unless there is a force from the outside to apply on this object to change its motion, okay. So this was actually realized by first, not Newton, by Galileo, okay. So Galileo was the first person who realized that the force is necessary to change the motion of object, but it's not the reason to keep an object moving with its velocity, okay? So he realized that in the absence of the force, so a moving object will continue moving with the same velocity. And Newton just refined it in his book, and then Newton made it the first law of motion in his book. And of course, he also gave credit to Galileo, all right? So a few points I want to make about this first law, okay? So when something's moving, okay, there may be many forces on this object, okay? Actually, it's really hard to find anything in nature that has no force on it, okay? But if the net force on this object is 0, okay, there may still be like 4, 5, 6, or even 100 forces on this object when it's moving. But if the net force on this object is 0, okay, this object will still remain at rest or continue to move with a constant velocity, okay? So at rest, it's just a special case of constant velocity, right? 0 is also constant, okay? So what Galileo and Newton realized is that no net force is needed to keep an object move at a constant velocity. Okay? So most people will feel like this is not that intuitive. This is sort of like counterintuitive. Like if I want to move something, I do need a force to keep this thing moving. Okay? Well, what Newton and Galileo realized that it's not like a force, it's not needed to keep something moving. Okay? You may still need a force to keep something moving. But what they realized is that if all the forces balance out, right, no net force is needed to keep something moving. And most people feel like that they need a force to keep something moving. It's because they don't realize some invisible forces, right? For example, gravity, friction force, right? If I want to move something, okay, here, I would definitely need to have a force to push it, right? So you would say, I do need a force to move this guy, to keep this guy moving. That's because there's a friction from the surface on this box, okay? And then what Newton and Galileo realized that if you want to keep this thing moving at a constant velocity, actually the net force must be zero, okay? So that is why if I want you to move something with a constant velocity, you actually should be very, very careful because you want to find the balance, right? So that the force from your hand is going to balance the friction from the surface exactly, okay? If you just want to move this guy, okay, you can apply a random force. But if you want to keep it moving at a constant velocity, the net force must be zero. That's why you should do that very, very carefully because you want to find a balance so that it moves with a constant velocity. The velocity doesn't change, right? That's because no net force is needed to keep an object moving at a constant force. So if something is moving at a constant force, the constant velocity, the net force must be zero, okay? And then, of course, if I lift this thing, right, I'm just applying force to balance gravity. If I want to lift this thing at a constant velocity, of course, you're going to do that very careful to find the balance because you want the lifting force to balance the gravity exactly, so the net force on this object is zero, okay? So a force, a non-zero net force is definitely necessary to change the motion of object, the velocity of an object. That's what actually a force does, okay? That's what the effect of a force on a moving object, okay? Before Newton and Galileo, no one realized that, okay? So think about basketball, okay? Again, I always use basketball in my physics class. If you pass the basketball to your teammate, right? How does your teammate catch the basketball? Well, your teammate is going to grab the basketball, right? When your teammate grabs the basketball, okay, they apply a non-zero net force on this basketball, which is not going to be cancelled by anything else, right? So that they can stop the basketball. They are changing the motion of the basketball from some velocity to zero. So of course, they will apply a non-zero net force on this basketball, right? If someone is in the other team, they want to steal the basketball, what do? They're just going to hit the basketball, right? When they hit the basketball again, they are using a non-zero net force to change the motion, change the velocity of the basketball. So in order to change the motion or velocity of an object, you do need to apply a non-zero net force, okay? So forces are vectors, so they have directions, right? That's how many forces on an object can cancel out exactly, so that the net force is zero and this object can move with a constant velocity, okay? So if you want to figure out the net force, you should be very careful. The best way is to draw all the forces on this object, okay? Draw arrows, okay? So that's called a free body diagram. We call that a free body diagram, okay? And then a very interesting conclusion from Newton's first law is this. If something is originally moving under an external unbalanced force, okay, say something is moving in a circle, okay, we're going to discuss circular motion in detail later, okay. Say if you are whirling something with a string in a circle, And somehow the force, so the string has a tension on this object in a circular motion. So that's why this object is going to keep moving in a circle. So it's not in a straight line, right? So there is an unbalanced net force on it. Okay. Somehow if this force disappears, okay, say the string breaks. So this is some experiment you can do to confirm Newton's first law. Okay. In that case, when the force disappears, okay, the object is not going to continue moving in the original direction. Okay, it's not going to continue moving in a circle as it originally does. It's going to start to move in a straight line. Okay, so it's going to start to move in a tangent direction. It's going to fly off in a tangent direction. It's not going to fly inward. It's not going to continue moving in a circle. It's going to fly off tangent with the continue with the velocity in a straight line. Okay, so I do have an experiment which is similar to that. It's not a string, but this is also a very classical experiment in this part. This is called a broken ring experiment. So I have a broken ring here, right? You see, this is a circle, but it's not full. It has opening here, okay? So what I'm going to do is that I'm going to shoot this ball to this broken ring. So it's going to enter the ring here, and because the ring is going to have a force on this ball, so it's going to keep this ball moving inside this ring. But once it reaches this opening, okay, that force disappears. There's no force from this ring on it. So it's not going to continue moving in a circle. It's not going to inward and outward. It's just going to go tangent in a straight line, okay, because of Newton's first law. So let's do that, right? It always goes that way. Doesn't matter how many times you do that. I hope you can see that in this video. Okay, it's going to, once it reaches opening, it's going to always go tangent, okay, with the constant velocity in a straight line. So that's Newton's first law, okay. All right, so that's that. So because this is a fundamental law in nature, so everything does the same thing, okay, everything does the same thing, okay. There's a natural tendency of every object to remain in a state of rest or uniform motion, okay. So we have a name for this tendency. We call it inertia. You may have already known this name, okay? So it turns out everything in this universe has inertia. Everything in this universe is going to try to remain in their own state of motion, okay? Unless there's an unbalanced force from the outside to change its motion, okay? So any object always has this tendency to resist changes in its state of motion. That's inertia, okay? And the mass is the only measure of inertia, okay? So the more mass an object has, the more inertia has. And that is why it's so hard to move heavy objects, because when you move heavy objects, you change its motion, right? So because they have a lot of inertia, so it's very hard to move them. So some people, they would say this, and this is not a very accurate. Some people will say that when like a truck is moving really fast, it has a large inertia, okay, compared to like a truck moving slow. They have the same inertia, okay? The mass is the only measure of inertia. You don't say when something moving really fast has a larger inertia than it is at rest. It has the same inertia, right? Because when it is at rest, it's still hard to change the motion of this truck, right? You still need a very, very large force to change the motion, change the state of motion of the truck when it's at rest. It still has inertia, okay? So you shouldn't say that something moving fast has a large inertia compared to things moving slow or moving things at rest, okay? If it's the same object, it always has the same inertia in any condition, okay, because the mass is the only measure of inertia. If the mass doesn't change, the inertia is the same. So another experiment, okay, another way you can confirm the existence of inertia is that there are things around us, okay? There are things around us you can use to confirm the existence of inertia, the Newton's first law, right? So Newton's first law says if there's no net force, if the net force on the object is 0. It continues moving in a straight line, right, with a constant velocity. We don't see that a lot in our real life, right? Because, as I said, they're always like, nature is really complicated, okay? It's very hard to have all the forces on the object totally balanced out, then the net force is 0. But there are special cases you can find that, right? For example, if you ever seen like hockey game, okay, the motion of the puck on the ice surface, okay, if you have seen like a hockey game, you always see that when the player hits the puck using the stick, the puck is going to continue moving, right, in a straight line in the original direction, okay, even after the puck has left the stick, right? So the player is just going to hit the stick with a very large force, then that's it, right? The stick, the puck is going to leave the stick, and then the force is not on the stick anymore, but the puck can still move with the initial velocity it has in a straight line until it's hit by another player, right, or another stick, right? So the inertia is the reason the puck is moving in a straight line, okay, with the constant velocity, because in this case the friction from the ice surface on this puck is really small. It's totally negligible. So if you draw the forces on the puck, you would only get these two forces, right? Take a look at slide 5. You will only get the force gravity on it, right? And then you, which is the we call it weight. And then you get a normal force from the surface on it, supporting it. And these two forces, they can cancel out exactly, so the net force on the puck is 0, okay? So that's why the puck can keep moving in a straight line with the initial velocity it has until it's hit by another stick, another player, okay? So, as I said, right, mass is the only measure of inertia, okay? If you have played swings, okay, compare a small kid and a fat guy on the seat, right? It's very easy to push the little kid, but it's really hard to push a fat guy, okay? That's because mass is the only measure of inertia, right? The fat guy, even at rest, not moving, still has inertia, right? You shouldn't say things that are moving really fast has inertia, right? They also have inertia when not moving, okay, because mass is the only measure of inertia. So to summarize, okay, everything in this nature is lazy, okay? We don't know why, but that's what we discovered in this universe. Everything tends to keep on doing what they're doing. They don't want change, right? Nothing wants changes, okay? All right? So that's Newton's first law. And there are actually a lot of everyday applications of Newton's first law. Okay, it's just a lot of people don't call it a law, right? It's some life-holding truths, okay, you believe because this happens. Every time this happens, okay, it's always the same, okay? And in physics, we call them laws. We call them laws. For example, think about when you're on a bus, okay? And then if the bus driver, slams on the brakes suddenly, right? What's going to happen? This is what is going to happen. You're going to fall forward, right? Everyone does that on the bus. You can't find any exception, right? Why does that? Why is that? Well, that's because of inertia, right? If the bus is moving this way with the velocity, you have the velocity with the bus, okay? So your body wants to move in that same direction with the same initial velocity it has. But if the bus stops suddenly, your feet are going to stop with the bus. But your body still has this velocity, still wants to go in that direction. So that's why when the bus stops, okay, suddenly your body is going to fall forward, right? And you can't find any exception. You don't find anyone standing still or anyone falling backwards. You don't see that, right? That's because of Newton's first law, right? That's a law in this universe. So it's true everywhere. It's true everywhere. That's why we call them laws. And that is also why, because of inertia, you should always wear seatbelts when you're driving, okay? Think about it, right? When you're driving, say on the highway, you're driving at 65 miles per hour. You get into some accident, unfortunately. Your car is just gonna stop, right? It's at a collision with another car, okay? Or a tree or something. Your car is gonna stop, like from 65 miles to 0, right? You were moving with your car, right? So you still have this 65 miles per hour, right? This velocity. Your body still wants to move at 65 miles per hour. If there's no force to stop you, you're gonna fly forward to the dashboard, to the windshield with 65 miles per hour. You may get serious injury. You may even die, okay? You need a force to stop you when you get into a car accident, okay? When the car stops, okay, suddenly, okay? Where does that force come from? If you wear a seatbelt, the seatbelt is going to provide you a force to stop you when that happens. So you're not going to fly at 65 miles per hour to the windshield or dashboard, okay? So you should always wear seatbelts, okay, if you live in this universe, okay? Because everything has inertia in this universe, no exception. That's why we call it a law. We discovered this law. Newton and Galileo discovered this law, okay? And we don't find any exception from this law, right? Now, let's take a look so I'm gonna use these small questions, quick questions to quiz you, okay? So take a look at the picture on slide 10. Does this image imply the bus is starting or stopping if this person leans forward and drops his phone? Okay, I hope this is an obvious one, right? Even if you don't know Newton's laws from your experience, okay, you should know this implies the bus starting or stopping, because this is always true, okay? You never find expression, you never find the opposite. You never find the opposite in your life. So what's your answer? This implies the bus is stopping, right? That's what we just discussed. When the bus stops, okay, your body still has the tendency to move forward with the initial velocity it has, right? So that's why your body still wants to move that way, but your feet already stopped with the bus, so you lean forward, okay? You never see opposite, okay? You never see opposite if the bus stops. What about the next picture, the next slide, slide 11? Does this imply the bus is starting or stopping, okay? If the person falls backward and drops his phone. Okay, so again, I believe everyone's going to have the same answer if you live in this universe, okay? The answer is going to be the bus is starting, right? When the bus starts, okay, your body initially is at rest, so it wants to stay at rest, but your feet already start to move with the bus, so that's why you lean backwards, right? If you live in this universe, this is always what happens when you're on a bus and the bus is starting, okay? If you live in a different universe, it may not be true, okay? But if you take physics in this universe, it's always like that. Now take a look at the next question. Take a look at this picture, okay? Slide 12. Does this picture indicate the car is making a left turn or right turn? Okay, think about it, right? So these two people, imagine you're one of them, right? You're sitting in a car and then you are the passenger sliding to the left of the car. Does that imply the car is making a left turn or right turn? Think about it, right? I'm 100% sure this has happened to everyone, right? All right, based on your experience, or based on Newton's first law, does this imply the car is making a left turn or right turn? Okay, what is your answer? This implies, okay, the car is making a right turn. Okay, how do you explain? First of all, if this is not obvious to you, next time when you're on a car, you're a passenger, okay, pay attention when the car is making a turn, so you know what's going to happen. Secondly, we can explain that using Newton's first law. So let's draw a top view. Let's draw a bird view. So it's easier to explain using the bird view. If you're looking at the car from the top, right? You are like in the cloud, you look at the car. Initially, the car is moving in this direction. When it's making a right turn, so the car is moving this way. It wants to make a right turn and go in that direction. You are sitting here, right? You're moving, initially you're moving with the car in that direction. And your body still wants to move in that direction. So you still want to keep moving in a straight line in that direction. So inside the car, you're going to find yourself sliding that direction. But actually your body is not sliding there. Your body tries to move in the same direction with the same velocity you already has. Okay? But inside the car, you're going to feel like you're sliding to the left. Okay? That's still Newton's first law, inertia. Okay? Again, next time you are in the car, okay? You're a passenger, pay attention when the car makes a turn. It's always going to be like that, always, if you sit in a car in this universe. Okay? If you go to a different universe, I'm not sure. Okay? All right, so take a look at the next question. So this is an interesting one. Okay, you're going to do some thinking. You ride up an escalator carrying a briefcase. The escalator is moving up at a constant velocity. Okay, what is the direction of the net force on the briefcase? The direction of the net force on the briefcase. Okay? Which one is the right answer? Think about it. I'm asking you the direction of the net force on the briefcase. Okay? So you need to find all the forces on the briefcase and then figure out the net force. Okay? Which one is your right answer? Okay? The right answer is this. There's no direction because the net force is 0. Right? Why? You can draw the forces on this briefcase, right? If the briefcase is moving with you at a constant velocity and everything is moving with this escalator, you draw the Free-body diagram of the briefcase. The briefcase has gravity, right? For sure. So I can draw gravity. You are holding this briefcase, okay? So your hand has a force on this briefcase. What is that direction? Okay, well, that's not that obvious to see. That's not that obvious because you don't see the force. Okay, you can feel the force. But even if you can feel the force, I ask you, give me a definite answer. What is the direction of this force? Well, it's really hard because you don't see that. That's when you use laws. Okay, when you work with things you don't see, you use theories, you use laws. You don't trust your senses because you don't see them. How do you work with them? Right? Do you see gravity? You don't, right? That's what I usually ask. Do you see gravity? Why are you sure gravity is on you and then it's always down? You can feel that, right? You can feel that. Even though you don't see that, you feel that. Why are you always sure the gravity is always down? Well, you know, I just feel that, okay? What about other forces, okay? You can feel that, but are you sure about the direction? Well, you're not very sure. You have to use a law or theory. So Newton's laws tell us, Newton's first law tells us, if this guy is moving at a constant velocity, it doesn't matter which direction this velocity is, right? In this case, the velocity of this guy is in that direction. It has an angle with the ground, but it's moving with the constant velocity, right? The net force on this guy must cancel out, okay? So the force from your hand on this force is going to be exactly this. Okay, and these two numbers, they're going to be equal. So that the net force on this briefcase is going to be 0. It's moving at a constant velocity. Okay, you have to trust the laws. Okay, because you don't see this force. You don't see this force. Okay, think about this. Okay, if this is not that easy to understand for you, think about this. I place this box of these markers here. There's a gravity on this marker down, straight down. That's the most familiar force to us. There's also normal force on this marker straight up, supporting this guy. If I want you to draw a Free-body diagram, you would draw it this way. Gravity down. And then the normal force, what's the relation between these two forces? I believe most of you can tell me these two forces are going to be equal, cancel out each other. But if I ask you, why do you think this force is going to be equal to this guy? Say this guy is like 10, this guy, how can this guy not be 9.99? Are you 100% sure it's not a 10 exactly? You don't see this force, you don't see numbers. Well, you would say that just makes sense to me. You are using a law. You are using Newton's first law, right? Because this guy is at rest. So your intuition tells you that the net force on this guy must be 0. These two forces must cancel out exactly, right? If this is 10, this must be 10. And this must be straight up, even though I don't see the force. I don't see it, right? No, it's straight up, okay? So when you don't see things, when you work with things you don't see, okay, you need to use a law. Some people use laws in their life. They just don't realize that. So in this case, it's the same as that, because this is constant velocity. The net force on this, if you believe that, you believe this, okay? The net force on this briefcase must be 0 so that it's moving in constant velocity, right? If you assume that the net force on this guy is in this direction or any direction, it violates Newton's first law. So it cannot be true, okay? Newton's first law is a fundamental law in this universe. We believe that even if you go to the other end of the universe, okay, you meet some aliens, they will discover the same law as Newton's laws, okay? They may phrase that in a different way using their own language, okay? But it's going to be the same law. So that's the answer, okay? That's going to be no direction because the net force is 0, okay? All right, so again, as I said, when you work with things you don't see, it's very tricky. You don't work with, you don't just trust your intuition. You use laws and theories, okay, which have been verified by experiments, okay. Now let's take a look at the next question. Again, I want to use this question to test your understanding of Newton's first law and inertia. If you push a book on a table, or push anything on a table, right, like this, it's not going to continue moving at a constant velocity, right? It's going to slide a very short distance, it's going to stop, right? Then in this process, which statement is correct? Take a look at these 5 statements, okay? Which statement is correct? It's the right one. All right, what is your answer? So let's take a look at each statement. A non-zero net force is needed to keep the book in uniform motion. Well, that's wrong. That violates Newton's first law, okay? A 0 net force is needed to keep a book in a uniform motion, right? If something is moving in a uniform motion, the net force must be 0, okay? B, the friction from the table brings the book to a stop. Is that right? That is right. That is the reason the book is unable to continue moving at a constant velocity, because the friction stops it. If there's no friction, if the friction is very, very small, almost 0, then the book is can continue moving with a constant velocity. Think about the puck in a hockey game, okay? Because the friction, if you can remove the friction, then it will be very easy for you to understand Newton's first law. It's going to be very intuitive. Newton's first law is going to be very intuitive to you, okay? It's just because the friction is everywhere. It's really hard to remove them. So we always see things like stop, you know, if there's no external force on it. That's because friction stops that. C, the book's inertia decreases as it slows down. Is that right? No, it's not right. As we discussed, the mass is the only measure of inertia. If the book has the same mass, the inertia doesn't change, okay? The inertia is still the same. So it doesn't decrease as it slows down. D, the friction from the table reduces the book's inertia. That's also wrong, right? Because it's the same reason as C. The inertia doesn't depend on other things, it only depends on mass. E, the gravity brings the book to a stop. This is also wrong, right? Is gravity on this guy? Yeah, gravity is on a book on the table, but the gravity is going to be balanced by the normal force in this vertical direction, right? The reason the book stops or anything you move on a surface is the friction. It's not gravity. Gravity is not the reason it stops. Gravity is on it, but gravity is balanced by normal force usually. If it's on the surface, the surface is supporting it. Okay? So this is Newton's first law. I'm going to stop here, and next time we're going to discuss Newton's second law.